What's that
Recording
about?
is on.
Because a compiler miscompilation is terrifying, but also really interesting. You put in the good code, but you get out, bad binary. Wow, right? So anyway, yes, that is now fixed. Thank you.
I was also hoping Scott would be here, especially since we were missing a speaker until last minute.
We have two now, so we're all good. We're all good. All right. So as usual, we get together to meet. There's a Red Robin that's near the old Sears that isn't there anymore. If you don't know where that is, don't worry, because that Red Robin is now closed. So now we can start talking about where the old Red Robin used to be, and people will also not know not know what we're talking about. So we will be meeting at the Redmond Town Center Red Robin. So if you jump on the light rail and take it east to all the way to the end, not west, you'll be in the right place.
The other Red Robin closed. How could that happen?
I like to think because we didn't go there anymore. That's right. That's right. I think it was the first night we didn't go there. They had closed the day before. So even if we had tried to go there that night, we would have been in for a rude surprise. So the fact that we just intended to stop going, told that group that they were not in our good books anymore. They were a bit of a hassle to go there, and so they were not in our good books anymore. So they just gave up trying to make a go of that business. So I like to think it was us.
There's another way the causality could have worked. They could have known the end was nigh and just started like months before, just putting out bad vibes.
That's true. That's true. Make it happen that much faster. All right. So tonight we have two talks. Oh, go ahead.
And the address of the Red Robin in the Discord now.
Yes. Thank you. Thank you. We have two talks tonight. One talk by Brian is testing Unsafe Rust. And then I will be giving a talk that I'm titling Rusty Code for Tiny Computers, running programs written in Rust on the Commodore 64. And it'll be good for all levels. And we'll do that after the break. All right. I think that's all we need to do for the preamble.
Oh, thanks. Okay, hopefully my screen share will work. Bear with me just a second.
So you're
and I need to get
you separately
need to get projected in the room.
And I will.
And I turn over the USB 3 times and then it plugs in.
We have to talk to the framework person who wants you to consider a laptop.
Okay.
Where's my Jitsi tab?
Bear with me, folks, on the internet. We need to get the room AV working. Here we go. Okay.
All right.
All right. Thanks, everybody. I'm Brian. Happy to be talking with you today. I'm going to share some of my recent learnings on testing unsafe Rust. This is purposely a talk about an area that's kind of new for me. As I've gotten into contributing to Rust projects, I've started to notice some patterns that got me interested in finding out what tooling was out there to help make my life a little bit easier. And so I'm happy to share, as I'm in my learning process, what I'm coming across. I'll talk about some tools and techniques and best practices for validating that unsafe Rust code works properly. And the context for this is, for a long time, I worked for the internet and spent way too many long days and nights troubleshooting C++ code that had weird memory corruption bugs that happened in 1 out of every 10 million requests, and really grew to hate memory unsafety. Then when I retired from all of that, I decided to spend some time contributing to open source Rust projects, and I liked what I saw. There was this shared mission of make critical software infrastructure memory safe so that it's less likely to have crash bugs and data corruption and security vulnerabilities. I'm all about that. And as I got into Rust, I found, wow, the compiler's my buddy. It's got this borrow checker that's pretty strict, makes it hard to write code that's going to compile. But if that code compiles, it's going to work. I'm going to be free at runtime from all sorts of horrifically bad things happening with memory that will cause me to stay up all night troubleshooting. Unless you use that unsafe keyword in your Rust code, which tells the Rust compiler what follows is a block of stuff that doesn't follow normal rules, and within this space, the compiler can't guarantee anything about the memory safety, and it's up to the programmer to get it right. And I noticed I was seeing this a lot more than I would have expected. Turns out it wasn't just me. The Rust Foundation did a study in 2024 and found out that 1 in 5 crates published on crates.io used some unsafe code, which was a higher number than I would have expected. And I found myself wondering, what in the heck is going on here? Wasn't the whole point of Rust to be memory safe? How are we getting all these projects with unsafe code? Is this just the work of people who started out as C++ programmers carrying forth bad habits when they go to Rust? Or maybe it's people like me who like to make their software fast, but we're getting a little too carried away with our raw pointer shenanigans trying to scrape out that last 1% optimization. No, it turns out there are good reasons why smart, conscientious engineers sometimes have to write unsafe Rust code. Maybe you've got a project that's predominantly in Rust, but you've got some functionality in an old C or C++ library. Well, it's straightforward to call it from Rust, but that means you're writing unsafe Rust code. Or maybe your Rust project itself is going to be a new, modern, secure plugin that plugs into some existing framework written in another language. The glue that binds those languages together involves you writing some unsafe Rust. Or maybe you've got to write some assembly language in line within your Rust code, like because your Commodore 64 doesn't have sound instructions without writing assembly. Or maybe you've got some functionality that's rare that you need. Maybe you're porting Rust to a new platform and you've got to write the atomic library that involves some very machine-specific instructions you've got to call into assembly for. An interesting case I've been learning about recently is people who are writing encryption code in Rust are tending to find that a best practice is to write it in assembly, which sounds weird, but there's a good technical reason for it. When you write encryption code, you want to run it in constant time so that no matter what your private key is or no matter what your clear text is that you're encrypting, the encryption process always takes the exact same number of clock cycles. Because otherwise, some very sophisticated attacker might start noticing, this message took longer to decrypt than that message, and start deducing things about what your keys might be. And so it turns out you can't trust compilers to generate constant time code, because compilers nowadays really love to optimize stuff. And there have been cases in the Rust cryptography ecosystem in the past where somebody wrote code thinking, this looks good, it runs in constant time, their code reviewers all agreed, yep. And then a compiler optimization meant that it no longer ran in constant time and was suddenly a security vulnerability. And so what's the solution? Well, if you write it in assembly and line in your Rust, then you're free from the compiler messing with your logic. But you just added some unsafe code in the middle of your Rust project for a good reason, but you're dealing in unsafe Rust. Or maybe you're writing code that's going to process a whole lot of data and you want it to be fast. And you want it to be as fast as possible on whatever computer it's running on. And if it's something that benefits from SIMD instructions, you might look at the hardware landscape and say, the newest, latest, and greatest CPU models sometimes have new instruction set extensions. Things like AVX 512 in the x86 world, where if you've got a very new CPU, it's got some additional machine instructions that process even more data at once in giant vector registers. And for certain applications, could be the right thing to do to get the most speed out of it. But then you think, darn, I want to be backward compatible. So I'd better put that code in and then the fallback code that works on any CPU. And then at runtime, I'll just choose whatever is the best that matches the available hardware. which is a pretty good practice. But to do that, you end up writing some unsafe Rust. So lots of good reasons why careful, conscientious programmers can find themselves writing unsafe code. And if you think about these examples, what types of programs involve these sorts of use cases? Low-level stuff. If you're writing an operating system, you'll probably have to write some unsafe code. If you're writing a networking driver, you'll probably have to write some unsafe code. Writing a cryptography library, writing an embedded controller. These are also the places where you really, really don't want memory corruption. These are the places where you want all those safety guarantees the most. These are probably these sorts of use cases that got you into Rust in the first place. But other tactical constraints mean, darn, part of your code base here is going to be unsafe Rust. So what can we do about it? Well, it's instructive to look at two different aspects of Rust. They get talked about together a lot, but they're different in a way that matters. First, there's soundness. If a Rust program is sound, it means it doesn't have undefined behavior. And there's a long list of what is undefined behavior, but it includes things like you can't dereference a null pointer, you can't have an object and then delete the object and then access it. You can't access the 5th byte of a 4-byte slice. All these sorts of things that safe Rust protects you from. So if your program is sound, it doesn't do those things, which also means it probably won't crash unless it hits a panic and crashes in a very safe, controlled manner. That's different from safe. Safe means the compiler can prove at compile time that your code is sound. And so if you're not using the unsafe keyword, if you're just using the other 99.9% of the Rust programming language, your code is safe, and therefore, if it compiles, it's sound. And you get all those good benefits of Rust watching out for you. And the borrow checker saves you from your own bugs. But what if we're in this little intersection slice of the Venn diagram here, where we've had to write some unsafe code for sound technical reasons, but we want our unsafe code to be sound. We don't want our bit of inline assembly or our C library that we're using or whatever to be causing memory corruption. What can we do, and what help can we get from the tooling ecosystem to achieve that? Because if we can achieve that, then we've got soundness, we've got code we can trust, which is what we really want. To help lead into a discussion of some tools that are out there that might be able to help, I brought along some unsafe Rust code and some unsafe C code that we'll integrate with. First, I wrote a little function that writes to a buffer. I used to be a C++ programmer once upon a time, and so I did what seemed natural here. I have a function that takes a raw pointer to my buffer, and you tell it how big the buffer is, and you give it a byte value, and it loops through, and it fills every byte of that buffer with that byte value. Pretty straightforward. What could go wrong? It's also really easy to write that in C, so I wrote a C version, and you can wrap that with this extern C declaration and call your C function from Rust. And since I've got a write function, might as well add a read function as well. So I wrote a sort of parallel read function, give it a raw pointer to my buffer, and I tell it how big it is. And here I loop through and compute a very simple checksum and return the checksum to you. Pretty straightforward stuff. What could go wrong? And here too, I've got a C implementation of the exact same logic. I can put this in an extern C wrapper and call it from Rust as well. But since I'm a conscientious programmer, I'll write some test cases. First, I'll test my read API, create a little slice here on the stack, 5 bytes, and then I'll use my read function to read all 6 of those 5 bytes. Now, some of you may be getting ahead of me here. Turns out that this is unsound and will lead to undefined behavior at runtime. I haven't written very good code here, I confess, but at least I'm going to test it. Next, I wrote some test code that tests a different scenario. Here I've put my data on the heap rather than on the stack. And I'll use my write function. I've got a 5-byte buffer on the heap, and I'll write to all 6 of those 5 bytes. And I'm sure that's going to go great. While I'm testing, there's some more unsound things that I can exercise. Here I'll make a buffer on the stack and then let it go out of scope when a function returns. But with some raw pointer shenanigans, I will keep track of where that buffer is that's now no longer valid and try to read it, which is undefined behavior. You can't do this in Safe Rust, but in Unsafe, you can do lots of crazy things. And there's a heap variant of the same thing. I can use a box that'll allocate memory on the heap, make myself this slice of 5 bytes here, then drop it so that it's deallocated, and then try to read it. Now, note that I'm being careful this time. It was 5 bytes, and I'm only reading 5 bytes, but still kind of sketchy because I'm reading something that I just deallocated. Super, super unsound. So with this little sample code base I've created, a read function and a write function, I created a test matrix of 12 unsound things that I can do with it. I can be reading or writing, and my data could be on the stack or the heap. And also I could be trying to access the data after it's already been freed or dropped or deallocated. All 12 of these are unsound. Safe Rust will stop you from even compiling if you try to do the equivalent of these in Safe Rust. But here in my Unsafe code base, it's up to me to make sure things work. So I've written unit test functions for every one of these 12 permutations in my test matrix, and I'll run my tests, and that'll show me the error of my ways. Ooh, oops. It seems all of my test cases passed. Since I'm trying to be a conscientious programmer, I'll also run a test coverage measurement tool. Cargo LLVM Cov will tell you your test coverage percentage for your code base, and it tells me I've got 100% test coverage, and they all passed. So this must be really reliable code, right? Oh, no, it's intentionally very broken code. There are 12 unsound memory accesses that I've put in here that all happen during the test execution. In a real code base, these are the sorts of things that could cause data corruption. They could cause a crash. They might cause security vulnerabilities. So I got a bit of a problem here. My functional tests didn't tell me how bad this code was. Now, in fairness, I got these fully passing results by doing a couple of tricks. If you looked closely at my test code on the previous slide, you might have noticed there are a couple of places where I put another buffer full of 0 bytes right before or right after the buffer I was overrunning to prove a point that functional testing isn't going to tell you with confidence that your unsafe code is correct. So if good old cargo test didn't catch the error of my ways, I need some better tooling. So what's out there? First thing I started looking at is static analysis tools. In other programming languages, especially in C and C++, there have been efforts over the decades to build static analyzers. These are sophisticated bits of software that you can point at your source code, and they'll analyze it and reason about it and get back to you with a report that says, at this particular location in your C code, you could be deleting an object in memory and then immediately dereferencing the pointer to it. Or here you might be accessing a null pointer, or there you might be stepping past the end of a buffer and accessing outside your object. These tools gained prominence in the C and C++ world out of necessity because those sorts of problems were par for the course in those languages. But in recent years, folks have started trying to build static analysis tools to analyze Rust code, because people, it turns out, need to use unsafe Rust for good reasons sometimes. And so there are a couple of them out there. I first looked at one called Rudra that looked promising. It started out as a research project by an academic group at Georgia Tech. They built themselves a very clever bit of software that can read your Rust source code and reason about it and tell you what's wrong with it, especially with regard to memory safety in your unsafe blocks. They tested it by pointing it at a whole bunch of mature open source Rust projects, and based on its output, they ended up filing over 100 bugs with those projects for previously unknown memory safety issues around edge cases. So kind of promising. Uh, Unfortunately, the research team that built it announced earlier this year that they're not maintaining it anymore, as they're having to move on to other projects. There's a snapshot you can find on GitHub, although it's x86 only, and I wanted to do some development on Mac, which is ARM based, so wasn't able to try that one. But I found another static analyzer for Rust, very spiritually similar to Rudra, called Kani, which I think is Japanese for crab, because Rust logo, crab, you get it. It's a project that was built at AWS. They've open sourced the tool. It too is a utility that you can point at your Rust code base, and it'll parse it, analyze it, try and reason about all the unsafe blocks, and get back to you with a report that says what could go wrong. They tested it by pointing it at their hypervisor that was written in Rust and a whole bunch of networking code that was written in Rust. Basically, in production, battle tested, mature, stable code bases, and it found problems in those, which is directionally a pretty cool sign. To use it, you've got to do some extra work. You need to write some scaffolding code to tell it where to start its analysis. And it doesn't support FFI. FFI in Rust is Foreign Function Interface, which is the, I guess, compiler nerd way of saying calls into other programming languages. So in my test code base here, where I've got some C code in my Rust project, it's not going to be able to help me with the C code. But let's see what it can do with the Rust code. You can use it by creating these little proof functions that look a whole lot like the unit test functions that I'm used to when writing Rust unit tests, except instead of a test directive at the top of the function, it's got a proof directive. And the key concept here is when you've got some input to an API function and you want the Kani static analyzer to reason about what could happen for different values of that input, you initialize it to this Kani any function. And that tells the proof engine inside of Kani, okay, think about what will happen to the code that follows for any possible value of this variable. What if it's 0? Analyze what will happen. What if it's 1? What if it's negative? What if it's being used as an index into a slice and it's smaller than the size of the slice? What if it's exactly equal? What if it's greater? What if it's infinity or maxent? And it tries to do this for all the data flows that might use this within the program. And it turns out pretty powerful. I wired it up for all of my scenarios in my test matrix of 12 intentionally broken memory unsafe test scenarios, and it started to find things. Here, for example, you can see it detecting that my read function that takes a raw pointer and a length, why it's completely unchecked and there's nothing stopping errant code from trying to read all 6 bytes of a 5-byte object. And so it detected that. Yeah.
Can you take a question?
Yeah.
Is this similar to fuzzing, or is it a parallel? Or
it's parallel. And in fact, question was, is this similar to fuzzing? And it's sort of a parallel track. And in fact, I'll talk about fuzzing some later because it turned out to be one of the things that helped me as well. The approach with Kani is it doesn't ever try to even run your code as is. It's rather analyzing and doing data flow analysis on your code as an object graph.
Okay.
But yeah, fuzzing, it turns out, will figure prominently in the very near future. So Kani, in its static analysis, found this particular example, and given my matrix of very broken things that I put into my example code base here, essentially found all the ones in pure Rust. Didn't have visibility into the C code calls from Rust, but still pretty cool. This was a simple, very simple test case for it, and I'm just starting to scratch the surface of what this tool can do, but it's something I'm excited to experiment more with in the future.
I have a question for you about how expensive did you find the annotations that you had to add to your code?
Yeah, good question. The expense of the annotations in this particular case, They were pretty easy because they were essentially just a straightforward translation of unit tests that I was already running.
Mm-hmm.
I expect that'll change for a non-trivial code base, though.
I see.
And there were other tools and research efforts I found as I was looking for supporting tooling out there, where I'd find somebody had done a research project and built themselves an engine that would prove assertions about the correctness of code, and they'd say things in their footnotes like, and we were able to validate our 1,000 lines of code, and we only had to write 3,000 lines of proof to do it.
Exactly.
This particular tool, the amount of code I had to write to get a static analyzer to work with it was on par with the amount of code I had to write for decent unit tests.
Okay.
So not trivial, and definitely an investment, but not outrageous either. Yeah.
In my experience, as long as you're only testing non-loops in your function set unsafe blocks, it's fairly easy. When you start getting into loops, especially if they're more than single-digit loops, it takes a very, very long time. And then also, I don't think their derived macros are quite there yet for non-primitive types.
Got it.
But
Thanks.
it's fairly easy.
Yeah, and that's a good point, that the tool is still in development, and you'll find code bases that it's going to struggle with and other code bases that it does fine. But yeah.
The one time I used it, I liked that it was easy to put in my CI, which was GitHub Actions.
Yes.
So going forward, I just knew this was always going to keep getting tested.
Yeah, exactly. What I like about this tool, and a lot more that I'll get to, is they plug into a CI pipeline in a pretty straightforward manner to just become a thing that you write the glue for once, and then on every commit, you've got the machinery looking out for you. But yeah, static analyzers for Rust still in their early phases, so might not work for your large, complicated code base. But we could look at dynamic analyzers. There are a lot of tools in this space. The C and C++ world has had dynamic analysis tools for ages and ages to try and help you find memory unsafety in those languages. And some of the dynamic analyzers work by taking your executable code, like your test suite, once it's compiled, and running it under an emulated CPU so they can watch all the memory accesses it's doing. Others work by tapping into the compiler toolchain to generate a special version of your code with extra check instructions inserted. Either way, these things work well, but they make your code run incredibly slowly. And because they're catching things that happen while you're running your tests, they're only as good as your test coverage. But these are a mature class of tools that are pretty widely available, and so are definitely a good tool in your toolbox. Let's take a look at a couple of them. Valgrind in the Linux world has been a go-to for a long time. It is basically a CPU emulator that will run your code and pay careful attention to all the memory accesses that you're doing, as well as all the memory allocations and deallocations, and therefore it'll notice things like, you're reading from this pointer that you just deallocated 10 minutes ago. You shouldn't do that. Or you've allocated an object that's 10 bytes and you're reading all 12 of those 10 bytes. That is broken also. Very, very valuable with C and C++ that didn't have a lot of language level defenses against unsafe code. Turns out this same utility works for Rust programs as well. It is Linux only. There's, I think, a porting effort underway to make it work on Mac OS, but it works on x86 and ARM Linux. Pretty straightforward to run. You just set some arcane, cryptic, horrific environment variables as seen here. What all this is doing is basically telling cargo test that when you compile the test executable and are about to run it, don't actually run that program. Instead, give it to Valgrind's CPU emulator and let it run it and let it scrutinize what's going on. And when you do, it starts to find things. Here, for example, it's found that in my buffer read function, the C version called from Rust, that I'm reading a byte beyond the end of it, which indeed was what my test program was doing that my unit tests didn't catch. And it helpfully gives me a backtrace to where in the program that errant memory access was happening, and then a backtrace to where the memory in question was allocated from. So, a pretty good find by Valgrind. Turns out that it is very effective at finding stuff on the heap. Less so, it turned out in my testing, less good at finding stuff that happened on the stack, which is probably less of an issue because in my experience in C and C++, you tend to use the heap more. Rust programs I've found use the stack a lot more. And so kind of a problematic blind spot. Although in its defense, Valgrind did have visibility into the C code being called from Rust, which is something not a lot of tools can do. If we have time at the end, there's also another very useful, cool application of Valgrind related to making sure your code runs in constant time, but that's a bit of a detour. So let's look at some other tools that can run our program and tell us if it's doing bad things with memory. Miri is a favorite in the Rust world. Conceptually, it's similar to Valgrind. It runs your code, watches all the memory accesses, tells you if things are going awry. It works in a significantly different manner, though. Instead of taking whatever executable comes out of your compiler and trying to run that and make sense of it, Miri instead taps into the middle of the compiler pipeline where your code temporarily exists as something called intermediate representation, which is half compiled code. It's in a structured data structure form, much easier for machines to work with than source code. And so it's a good format for doing things like optimizing on or data flow analysis or checking for unsafe behavior. But it's not yet translated into the final machine-specific assembly code. And so it's kind of an appealing artifact to work with because it's still got enough of the context about your Rust program that it has a fighting chance of knowing about variables and objects on the stack and those things that Valgrind had trouble getting visibility into. And the fact that it's not yet machine-specific assembly code means it's a generic format, and so the people who made Miri could build the engine once to run it and evaluate it, and it works on essentially everything that Rust works on. So great for portability of your development tools. Miri unfortunately doesn't in general support analyzing calls into other languages. So if you've got some C or C++ code that you're calling, it won't be able to make sense of that other than a couple of very special cases of like things in the C standard library that it understands because they're used so much it has to. But Miri, super easy to use. Instead of cargo test, we'll say cargo Miri test and run it, and it too starts to find stuff. Here it's finding that I've read beyond the end of an array on the stack this time. And I want to call out Miri because it carries on the Rust ecosystem tradition of very human-friendly error messages from the dev tools. Recall that Valgrind gave me a lot of hex numbers in its backtrace. Here, Miri is showing me the line of source code where the problematic unsafe memory access occurred. It even underlined the exact pointer dereference that was the problematic one. And it showed me the line of code where that object being accessed was allocated. So really, really powerful in terms of usability, in terms of telling you what went wrong and where you need to start looking to be able to fix it. And Miri did great at finding things going wrong on the stack and on the heap, just had no visibility into my C code. So we got Valgrind that was great at finding problems in Rust or C, but blind spots regarding the stack, and then Miri blind spots involving my C code, but otherwise could catch any errors happening anywhere in memory. We should look at some other options. Address sanitizer is one that's out there that came about in the C++ world as developers of C and C++ compilers realized that their users, the people writing C and C++ code, were forever struggling with memory safety because those languages don't give you a lot of guardrails. And the compiler developers realized, hey, while we're doing code generation, we could actually have an option to insert some dynamic checking code as we're generating your machine code for your program, so that if you're dereferencing a pointer, we could silently generate the code for you so that right before your program dereferences that pointer, it would check, okay, is that a pointer that I've recently allocated and then deleted? Was that a pointer into an object I recognize? If so, is it really in the object or has it strayed beyond the end of it, etc.? Sorts of things that you take for granted in Rust. This tool does, yeah.
It kind of almost sounds like a garbage collector, but like not the collection part.
Kind of, yes.
Sounds like garbage.
Yeah, a good point. In order to do its thing, it has to do some of the tracking analogous to what a garbage collector would do. And so that does give it overhead, both that it's got to do its bookkeeping of what memory is active and where, and watch every malloc call and every free call and match them up and such, in addition to all the extra conditional statements it's got to put in there for if bad memory access, then print error, etc. But it turns out all that overhead is still less overhead than Miri or Valgrind, which are basically running your program under a CPU emulator. Yeah.
Just a quick thing, it's also supported on Windows now.
Ah, nice. ASAN is now supported on Windows, which is awesome. So all the major platforms, I think, now have it available. And because it grew out of the C compiler world, works with C code, happens to also work with Rust code, because Rust C uses something called LLVM as its backend, and LLVM is also the backend code generator for Clang C compiler. And
that's if you're using the Rust C compiler. What about
Yeah.
the new Rust C, which doesn't? The other one is I'm like, okay, so it works with C and Rust. What if I want to like zig into this thing? Because I've been looking at zig and going, yeah, it's not for me, but if I have C, I'm going to write in this instead.
Yeah. A good point. So with Rust C, you get easy access to ASAN. Yeah. So the question was, what if you're using a different Rust compiler? Because there are other Rust compiler projects, and they won't all use the same compiler backend. And so, yeah, you may have to be using traditional Rust C to take advantage of ASAN. And what if your other code that you're integrating with isn't C? What if it's Zig or something else? Depends really whether those compilers have support for ASAN instrumentation. Because if they do, if you've got a bit of code in some other languages and you're linking it to your Rust program, if all the compilers involved understand how to do this ASAN extra instrumentation, then they all produce their object files, their .o or whatever, depending upon your system, that all happen to know how to watch over their parts of the memory access. And then when you link them together, you get full coverage. Otherwise, you might only get partial coverage. You might see that only your Rust has ASAN coverage. But ASAN, pretty straightforward to use. You just need some more horrifically arcane environment variables here that are basically telling Cargo, when you get to the point where Rust C is doing code generation, you need to turn on this special mode that puts the extra checks in the generated code. And so when you do, you can run your Cargo tests and it'll start to find stuff. Here it's catching a read overflow on the stack, telling me where the program was, gives me a backtrace to where the program counter was, and doesn't honestly do quite as well as Miri. at explaining where in the code I was and what data structures were involved, as it's multi-language. It tells me things like, oh, there's a bad address at a point that's X number of bytes from the frame pointer in your stack, which is true and valid, and I can't fault them for correctness, but not quite as developer friendly, not quite as human friendly as the Miri presentation. But this understands C code. And so it was able to catch all the permutations in my test matrix of intentionally bad code. So for a hybrid code base, it can be a powerful tool. But we've got these various dynamic analysis tools that can catch bad things quietly happening in your unit tests. They're all really good at catching the bad things that happen if they happen, but really they're only as good as your test coverage. What can you do to amplify your test coverage? Well, one option is fuzz testing. And I've seen a lot of projects adopting this of late. The idea behind it is generic. It can work for any programming language. It isn't just for unsafe Rust, isn't just for Rust. The idea is take your program, run it with randomly generated inputs, and see what happens. Which I acknowledge sounds kind of crazy, but in practice it can be very powerful. And part of the reason is it's easy to generate lots of random numbers and call your functions with them as inputs so that there's strength in numbers. You can have a fuzz testing tool that runs 1,000 or 1,000,000 different randomly generated sets of inputs. Still non-deterministic. It's its very nature, but probabilistically, because it can do random things in volume, the more of them you do, the more effective it becomes. And there are lots of case studies out there of people who've had well-reviewed, well-written, well-tested projects. And when they added fuzz testing, they were able to find obscure edge case bugs. And so we can give this a try for our intentionally bad example Rust code base here. There is a little bit of extra glue work needed, because we got to somehow generate random inputs and call my functions with them. There's a utility called cargo fuzz that'll do about half of the heavy lifting for us. And the way it works is sort of similar to Connie, where we had proof functions. Here we have fuzzing functions, and they all look kind of similar to unit tests. Instead of being wrapped in a test directive, they're wrapped in this fuzz target macro. And the arguments to this macro indicate what data types I'm going to need some random values of to pass into my API. And so to make this simple to implement, I just said, well, I'll use a fixed size buffer here to read, but I'll ask the framework to give me random values for how many of those 5 bytes I'm going to read. And I did this for all of my read and write use cases and ran the fuzz tester, and it very quickly found memory unsafety, as it didn't take it long to generate random values bigger than the 5 that was the maximum safe size of my buffer. A couple of things to note here. First, Cargo Fuzz ran ASAN for me automatically, which was really cool, because it might be the case that you've got some bug in terms of memory safety, which is definitely a bad bug, but not bad enough to immediately crash your program. If you've got ASAN plugged in, which Cargo Fuzz does automatically, when that bad thing happens, it'll catch it immediately and it'll log it as an error. And so you get better visibility without having to wait for something to happen that's a bad enough memory indiscretion to cause a crash. Also, the error that I got out of the fuzz testing as caught by ASAN is very technically correct. There was a bus error, and it hopefully gives me a program counter and a base pointer and a stack pointer, and I think T0 is caused by thread 0, and this was, I'm reading here, caused by a dereference of a high-value address. and it helpfully tells me to disassemble the provided program counter to learn what register was used. Oh yeah, I'll get right on that. Not not the
You call it a
easiest thing to use.
meditation error.
Yes. Some of the error messages you can get out of fuzz testing will be much less human friendly than you'll get out of some of the other tools that we've looked at. There is a technically sound reason for that. In this particular case, I think what happened is the random value the framework generated was probably something like read the first million bytes of this 5-byte data structure. And so it not only walked off the end of the data structure, it walked off the end of the memory page and probably the one after that, and at some point hit a page of memory that was invalid and got an error deep within the CPU's memory management unit saying, oh yeah, I don't know where you're trying to read, but there's nothing there. And at that point, it might not be anywhere spatially close to the address of the object that it had started with. So it wasn't able to easily say, oh yeah, you're trying to read 1 byte beyond the end of this thing. In its defense, I think that's probably what led it to be so arcane, but kind of an interesting combination of very powerful tool, a little cryptic to make use of at times. But very effective. I didn't try to use this for my use after free cases because the way I coded those in the unit tests, they were guaranteed to happen with 100% probability. So I didn't need random number generation to trigger those. All the others I tested with fuzz testing, and it caught them all, whether they're in C or in Rust, and whether the data is on the heap or the stack. So it can be a powerful technique. And again, not just for unsafe Rust, not just for Rust. Fuzz testing can be useful if you've got any program with complex inputs or complex internal state. And so I've seen a lot of projects that are building things like parsers that find it useful, or network stacks where you never know what somebody is going to send you. And so generating a whole lot of gibberish can be a good way to find your edge cases. But we've looked at a whole bunch of tools here. They've all had some kind of limitations, some kind of drawback. I ran into compatibility problems with some of them where they didn't work on certain systems, or they wouldn't work with certain programming languages you might be incorporating into your project. Some of them required me to do extra development work to write glue functions. Many of them made my unit tests run super slow. Some of them, like the fuzz testing, non-deterministic. Some of them, like Valgrind, had false negatives, which is concerning. But remember where we started. We started out with my functional test suite that I measured as having 100% test coverage, and every test passed, and it found 0 of my memory unsafety bugs. And every one of these tools caught a significant number of them. And so bringing the power of this extra tooling into my development process caught stuff that would have been really, really scary if it had gone into production code. But which one to use? Lots of choices here with different strengths and weaknesses. I'll start assuming you've got some kind of solid foundation where you've got a project that does good peer code review, and you've got continuous integration, so every commit gets passed through a CI pipeline with regression tests running. That's good, not just because it's a good practice, but because that continuous integration pipeline becomes your place to hook in these other tools so that they can become just part of your standard everyday development process. Next, if I think about memory safety from a security engineering perspective, I like the idea of defense in depth. When you've got a hard problem and a bunch of solutions that all might be 99% solutions for it, have multiple layers of defense. And the good thing is, since these tools are all nicely scriptable and can be easily plugged into your CI system, you can use a combination of them. So if Connie works well for your code base, you can plug that in, run that on your commits, get a static readout of are there things that its analyzer could find. But you can also run a dynamic analyzer For pure Rust, Miri works really well, very user-friendly, very thorough coverage. If you're using a combination of Rust and C or Rust and C++, you're probably better off using ASAN so that it can cover your whole code base. But one of those two can serve you really well. And then fuzz testing is, as I've come to look at it, a way of burning something that you've hopefully got in abundance, which is CPU cycles on your CI system, in order to achieve something that's harder to obtain, which is coverage of really obscure edge cases in your test matrix. And so it's a pretty straightforward thing to add, again, depending upon the complexity of your code base. And so I recommend doing a combination of these, wire them all up in your CI, and hopefully that combination will help you ensure that your code, even though it has to be unsafe, can still be sound. Do folks have other questions or ideas? Yeah.
Well, I'm just going to make an observation of just how fast computers are. I was doing a project with, we only had to deal with a single floating point number. We wanted to do an exhaustive test. So we did nightly so we could do F16, of which there's only 32,000 or something like that. So that was fine. It was like, hold it, I've got 16 processors. I can actually do F64 and go through 4 billion combinations, not
Yes.
with two things going in, but with one that only took a second.
Exactly. Yeah. We've got, in a lot of environments, we've got abundant computer power. And so this is one way to spend it on a good cause. Another thing I've noticed is
I agree wholeheartedly.
Another thing I've noticed is some of these tools, especially the dynamic memory analyzers, make your unit tests run very slowly. A practice I've learned from maintainers on a couple of open source projects that do this is divide your unit tests into small pieces. If you've got one function in your unit tests that takes 20 seconds to run, it might take minutes to run under Miri. And that's a big enough time measurement that you'll start to notice, and people will get annoyed that you're slowing down the builds. But if you can parallelize that or break that up, computers are getting wider in the sense that they've got lots of cores now, and you probably have lots more machines at your disposal than you used to. They're getting wider quicker than they're getting faster. And so parallelizing your test cases can make some of these tools very reasonable to use, even if they have an order of magnitude slowdown. Yeah.
Apologies, this is like semi-comment territory here.
Yeah.
But a lot of these tools don't find things like thread safety issues.
Yes.
Miri notably usually does, but there are tools out there that help you find thread safety issues. One that I like to recommend is Loom, which is, it's like a Rust library, but it gives you primitives that you can replace the regular like mutexes and things in your program with, and it'll exhaustively test all concurrent orderings of those things to try and reduce errors.
Nice. Thank you so much. So Loom, Rust package for testing all the permutations of orderings in your multi-threaded code. One thing I love about doing talks like this is when I learn new stuff. So thank you. There's always somebody in the audience who says, "Oh, I've got another cool tool that you should use." So thank you. Other questions,
I
thoughts?
think we better for time.
Oh, all right. One more.
Local model, using local AI or LLM.
Oh, AI. Yeah, sorry. I didn't attempt to use AI for this, mostly because I started out wanting to stick with deterministic tools. But yeah, I know that's a whole new area that people are starting to explore. And there's, gosh, for somebody who is interested, that could probably be a good follow-up talk someday, because I'd love to learn about it. Yeah. Awesome. Thank you so much, everybody.
Thank you, Brian. All right, so I have a 10-minute break, but we're running a bit behind here. So let's go with 5 minutes for refreshments and stuff. And when you come back, we will get started. find.
Also, if anybody's interested in some cutting edge fuzzer stuff, there's a Rust library called libafl, and that's where a lot of like fuzzing research is going into at the moment for like cutting edge, like concolic execution, symbolic stuff, mixes, and all that. And it's a very customizable modular library for fuzzing rather than just like a CLI tool.
Nice. We should start a thread on the Discord and seriously like collect these, because there's all these tools that could be really useful to somebody.
Let's test, because I have no idea. I have no idea what is going to happen.
Plug in the HDMI on your Commodore.
That's right.
Well, you're not going to be running Jitsi on the Commodore.
What do you mean?
It's crazy to think our little POs more power than you run it now.
This is a P32 Classic.
Oh, there you go. What did you build?
A robot.
Does your Commodore have a sound card?
Literally, no.
Well, it's
Does it have sound? Yes. It has a sound chip.
Because I know
There are no slots
I
on
know,
a
like,
64.
Commodore sound cards are very like sought after because there's only a limited supply of them, and the manufacturer doesn't make them anymore or something.
You're talking about the chips?
I think so.
Okay. Yeah, the SID chips are out of production, and they are legendary for 8-bit sound in the 8-bit sound area. And so there are several people trying to literally recreate the SID chip so that you get cycle accurate sound out of it. And it is a very difficult, because there's analog parts of the chip and everything, and it doesn't sound the same. So there's people with the schematics out and all the things to getting it just so. Yeah. This is not an original, because this is why
It's got USB ports on it.
I can plug HDMI, right? And if this was back in the day, this would be RF, and you would like see all kinds of nastiness. But this is far easier to present from with modern connectivity. No, it is not. It is neither of those. It's called the C64 Max. So it is inside, there's an emulation. It's a hardware emulation of the C64. And you'll see some capabilities that I will bring up that aren't on a normal, C64 in order to emulate like a 1541 disk drive and things like that.
Did they make an Amiga version of that? They have a legit Workbench license.
They do make an Amiga version of this, but it's the Mini. This is the Maxi. And so the Maxi has a working keyboard. The Minis are like quarter size, and they don't have a working keyboard. So you have to use an external USB keyboard.
I want to know something I can play Barksdale on again.
Yeah, you sure can. Yeah, that'll work.
It's something.
That'll work.
Have you run any demos on it?
Oh yeah, it's. I mean, I wouldn't necessarily say it's cycle accurate, but I haven't seen anything yet that's going to fail. Like exotic copy protection based on half tracking and other hardware tricks that they used to do on the floppy drive are obviously not going to work. But software-wise, it's indistinguishable from the original. So if you know any of your old reset command, for example, if you've got these numbers memorized, it does all the things and then resets, and you can change the color of the borders and do all this stuff. So I think we'll get started. Who here has never written in BASIC before? Okay. So I'm going to start my talk with an introduction to BASIC. All right. So here's what we do. I can't see what I'm doing. And this keyboard is hard to type on because everything is just subtly off where it should be. So BASIC starts with line numbers. So today we just write code and it falls through. Well, I guess that was too hard back in the day. I don't understand. But you have to write a line number. I could start with 1. but traditionally you start at 10 and then you go up by 10 because later you realize you forgot something and then you go back and if you want it to happen before 10, you call it 8 or something. You don't want to do 9 because what if something needs to go between 9 and 10? So you sort of like divide and conquer. But that's how we did it. Like this is it. So you start with line 10 and you say print okay. And then what we'll do is
Run it.
the famous, oh yeah, you got to run and then it prints, right? So there's your first basic program. So most times people want to see some action. So you say line 20, go to line 10. So there's your flow control. And when you do that, it's going to print over and over and over again. And it will never stop. So when you started playing with your computer and you saw one on at a store, this is what you would see, right? On the store, some kids would come in and they would write like their name and they would be printing all over the screen. And if you got fancy, they could change the colors. But you were playing with text, you were manipulating, code in this way. So very accessible. I mean, BASIC is an acronym. Beginner's All-Purpose Symbolic Instruction Code is what it stands for. But the idea was it was supposed to be approachable by everyone. And this was supposed to be the language that people would start using computers with. So the computer comes with a basic interpreter built into the ROM. And you would start doing this. There's no disk operating system. There's none of that. It just starts and it runs BASIC. You might have a cassette drive hooked up to it. You might have a floppy disk drive hooked up to it. Again, this machine has a grand total of 64 kilobytes of memory. So it's not, although you can get them today, but, it's not running hard drives or anything like we would know back in the day. All right, so that's our quick crash course on the Commodore 64 and writing in BASIC. So that cable is not quite long enough. All right, am I still in the group sharing my screen?
I don't think so.
That's weird.
Well, we saw the slide come up.
Yeah, I also want to share the screen so that the folks at home can see it. And
Here you go.
all right. Okay, so very quickly, I'll go to here. And I have no idea how to full screen. Play. There we go. Okay, so welcome to my talk here, Rusty Code for Tiny Computers. This talk is an early version of a talk that I will be giving in the future. You guys are getting your first look at it. It's inspired by a guy named Jason Turner, who did some amazing stuff about 10 years ago with, I think his talks were called Rich Code for Tiny Computers. And what he would do is use C++ and run it on a Commodore 64. And I was like, well, wait a minute now. I mean, can I run like my favorite language on my first favorite computer? And so that's where this was born. And ultimately, this is going to go where his talk went. If anyone's curious, hit me up on Discord. I can point you at the CPPCon talk where he gave it. It was impressive, and my hope is to one up that talk. Not tonight, just this is the intro. So that's where we are. So the format of this talk is going to start with a little bit of an intro. I want to introduce the basic hardware that we're working with. I think most importantly, it's the 6502 family of processors that are, I think, important to know about. How difficult it is to compile for that platform right now. And then talking about the LLVM MOS and Rust MOS projects. And then from there, we'll go into time permitting up to 3 demos of some code where we'll write some code in Rust and run it on the 64. All right. So let me see. I don't think I'll do this. So talked about that. All right. So we just talked about the Commodore 64. In current dollars, this brand new was $2,500, which is shocking. It had 38K available for basic programming, a little bit more if you were going to program it in assembly language. But the heart of this thing was something called a 6510, which is essentially a 6502 processor. We don't need to worry about the differences in the model numbers. They had the same instruction sets and so on, slightly different metal that they used, and they turned off one of the pins to use it for something else. But it's essentially the same part, and it's known worldwide as a 6502 is the thing. So you'll hear me call it a 6502. So the 64 claims to this day to be the world's best-selling single model of computer. Every other computer that has sold, it has sold well. It wasn't a single model. And so that might actually even be true. So I think that's kind of impressive for this to hold on. As I said, it was my first computer. I fell in love with it. It trained me well, if you will. And I've enjoyed low-level programming ever since. It has a whopping 3,500 transistors in here. Can you imagine that many transistors? Wow, that's crazy. So we'll be writing code in Rust. Rust will be compiling that to binary, and then we'll be running the binary on the Commodore 64. So if we take the machine language that the compiler emits and then back it up one level to assembly language, that's just the human readable equivalent of machine language. And so I would like to just sort of walk you through an example of what what assembly language looks like relative to Rust code. So the Rust code is basically iterating through the number 0 to 255, and we are going to push the current value into a very specific memory location. D020 in hex or 53280 in decimal. If you've written on a Commodore 64, you'll know these numbers off by heart. They're like your friends. You can like speak in numbers because that's what you had to do. That's the screen border register, and you can see the light blue border around this frame. That would change color. And because you're running this as fast as you can, the 64 is not waiting for the scan line to finish, and you would get like these rainbow colors. And so if you're doing any sort of demoware, or you're some sort of elite programmer doing questionable activities, maybe some of your software will introduce itself by using some of these techniques to razzle and dazzle and show how fancy you are in running the computer. So we're just writing an incrementing value to the exact same memory location as fast as we can, and then we're out. Now on the other side, on the 6502 side, this is going to get into why LLVM had such a hard time writing a compiler to target the 6502. When you're writing an assembly language, you have to think in terms of registers. So when we code, we think in terms of variables. Well, variables are an abstraction over registers. So if you're writing a program and you have 5 variables, you would just think that's stored in memory. Well, memory is very slow. Can be many, many times slower to access what's in memory than it is to access what's in a register, or what we might say in modern terms, what's in a cache. So cache memory and register memory are exactly the same thing. They're static RAM running 1-to-1, same speed as your CPU. There's nothing between the CPU and that memory. It can read that static RAM every clock cycle. That's not true with dynamic memory. You're dealing with a memory bus. You have to put some information in there. You have to wait for the lines to settle. It can, in certain implementations, it can take hundreds of times longer to read from dynamic memory than it does from static memory. So if you want your code to run fast, you want your code in static memory as soon as you can, or as much as you can. So the 6502 gives you a whopping, count them, 3 registers. So imagine writing a program of any sophistication where you have exactly 3 variables. You can't have 4, right? That's tough. So what it will do, I mean, you may have heard of register spilling, you may not have, but what you do after you've used 3 registers, you have no choice. You have to just, I need 4 things. I'll take one of the things that I have in my register and I'll write it out to memory. Slow. Then I'm going to read the 4th thing I need in from memory. Also slow. Then I'll do the thing. Oh, now I need that 2nd thing back. Okay, I'll get rid of something else that I don't need. And you're literally juggling 10, 20, 30 balls with exactly 3 registers in and out of memory.
What about the caches?
There's no cache. L1 cache, L2 cache, none of that. Okay?
Yeah.
You got 3 registers of static RAM, and then you got memory. So very simple processor. So what's going on in this 6502 assembly language? First line, LDX, load into the X register. You have 3 registers. They're called A, X, and Y. A is called your accumulator. It's the fancy one. It can do the most. X is the next fanciest one. It can do some cool stuff. And then Y is the weakest one. Why? Because they only have 3,500 transistors. And so the 3 registers are not even symmetric in terms of their capability. So you have limitations. So if you need to do certain things, they need to go in certain registers. You don't even get a choice. Otherwise, you have to spill your registers out to DRAM and put the data in that you need. So for now, what we're going to do is we're going to load into X because the value is 0. So the number 0 is going to go into the X register. Then we're going to declare a label called loop. Doesn't do anything other than it says this is a place I can get back to later if I need to, or jump forward to if I need to. Now I'm going to load into the accumulator let's see, which is load colors, comma X.
I think that moves X into colors.
No, it doesn't have 6502 doesn't have memory to memory.
No, I mean X as in the
X,
register.
Yeah, the X register should go into the accumulator. What the heck is that? Oh, that could be an offset because LDA has an offset capability. So it's colors is a value, right? It's like it's the 53280 perhaps. No, that's the D020 next. What the heck is that? I'll have to check that code because I'm not 100% sure that's right. But I guess in principle, what we want to do is we want to load the number X into I'm going to increment X.
It's using X as an index.
Yeah, it is using X as an index, but I don't understand why color's in there. Because basically, if we load the number 0 into the accumulator, the next instruction, store the accumulator into D020, will actually write the number 0 into that memory location. And then we're going to increment the number we want to store, and we're going to go back to the loop, and then ideally we should just increment the accumulator, right?
Colors into an array.
It's not that smart.
Are
Nope.
these 1-byte registers?
They are. They're 8-bit registers.
Is
And
color supposed to be another label for if the load fails?
nope, there's no conditional. There's one conditional at the end. It's like stop looping. That just may be bad code.
What
So
is colors? What is colors represent?
it's not defined here. So I don't know that that's a legal instruction because that to me looks like we're indexing from colors, which doesn't make any sense. So really what we want to do is we want to load a value like an X. We can store it in the accumulator, or we can store it, instead of STA, it'll say STX, D020. We're going to increment X, and then we're going to keep doing that. So we're going to store 0, store 1, store 2, store 3, and that will go cycle through all the colors in the border. Okay. So we've got this concept called a memory map, which will be very important for our Rust code.
Oh, just
Yes,
a
Benny.
question.
Yes.
If the register's at 8-bit,
Yes.
how does it index 16-bit of memory?
Oh, the registers? Okay, so the 64 has 8-bit data registers. So every register only holds 8 bits, 0 to 255. But addresses are 2 bytes long. And it will, so you'll see like store A here, D020. So it'll put 8 bits into D020 because every memory location is 8 bits wide.
So if you want to like address, if you want to dynamically create an address, how would you go about doing that?
You need 2 registers of your 3 registers.
All right.
This is the thing about it. It's very simple, right? There's no shenanigans here, right? And so if you wanted to store an address in memory, that address takes 16 bits. Your registers are only 8 bits wide. So you have to use 2 registers or 1 register sequentially. And so you could store the high byte, the format that the 64 uses is high byte first, then low byte second. So it's big endian. And so you would write to D020, and then the next loop or the next iteration, you would write to D021.
But like, let's say you want to write to an array, you don't do you hard code where that array is in memory?
Okay, so for example, like there's an instruction store accumulator D020, comma X, and that instruction will write a value from store the accumulator into the memory location plus that offset,
That's right.
and then now you can iterate through. But you're only going to be iterating by 1 byte each time, and unless you change the accumulator each time, you're going to be storing the same value each time. So a clear, for example, is you could loop very, very tightly with an offset.
The
Carl.
AI thinks that colors is an array here that was defined somewhere, and that I is your X is your index.
Yeah, except we are not writing to multiple locations. We are writing the
As you're
same.
reading that for some reason you've defined a 0 to 255 array, and now you're saying, give me the 0th element.
Yeah.
Zero.
That's what it means, but that's not what the code should be doing. So
Okay,
this
yeah,
is just bad code. So
Okay.
what we want to be doing is writing. Basically we can take out the LDA colors, comma X line, and change the next line from STA D020 to STX D020, and then this would be correct. All right. So this is a memory map. And what a memory map is if you look at all the memory in the computer as a big chunk of stuff where you can write your memory, it's not just RAM from 0 to 64K. There are devices in your machine that make sound, that make graphics, that do things, read and write from the disk drive. And so those have to be, how do you talk to those? You talk to those by pretending that they are memory. And if you know where they are, you use their memory address and you write numbers to them. Maybe 1 means read and 2 means write. We're talking to what's called the VIC2, Video Interface Chip version 2. The VIC-20 ran on the VIC-1, the first video interface chip. So the Commodore 64 got the V2.0, right, of the VIC chip. And so the VIC-2 chip is running, is set around D1000 in memory somewhere. And if you start what we say poking, or you start writing to those memory locations, you're going to be telling the VIC chip to do things, which is exactly what we were just doing. You see how we were writing to D020? Well, we're telling the video chip, the register 20, right, on D1000 is telling us to write to the border. Register 21 tells us to change the color of the screen, right? There's a whole bunch of registers, or a whole bunch of memory locations that the VIC2 chip will respond to with a fixed function. So when you're programming in assembly language, you need to understand your memory map. Here's where there's just RAM, and here's where there's other devices that I can use to make my machine sing and dance. Okay, so I think that gives us a pretty good intro to what we have to do in order to write a program on the Commodore 64. So what I'm going to do now is I'm going to move over to an editor, and I'm going to write a hello world. remember, this talk is inspired by rich code for tiny computers. So I'm actually going to go out of my way to use abstractions to make the code as high level as possible in the source. And we're going to see what the compiler does. Compiler 1.97.0 notwithstanding. Yes?
Can you just increase the text size?
Oh, I sure can. How's that? All right. So what we're going to do here is this computer, it predates ASCII, if you can believe that. I mean, ASCII existed, but it wasn't a standard yet. So this computer's text standard, let alone Unicode, right, is called PETSCII. And so it's different than ASCII. And we will probably not run into problems today because I'm handling those for you. But just know that, the standards that we take for granted today and have built upon so that we don't even think about it anymore, we're not standard yet. So we are clearly not using the standard library. We are clearly not parsing Unicode or UTF-8 strings, right? We don't really even have a heap per se. It's just memory. So this is really a no-stud or a bare metal development environment, much like writing on a Pico. So you can see us talking about no-stud. I'm telling the system where the main is, and this main is the equivalent of the C version of main with argc and argv. Yes?
Did you say if there's like a video buffer?
There is a video buffer, 1024 bytes, yes. Yeah, and it takes characters, and you can redefine your character set to make graphics. So yeah, it's quite primitive. So what we've done here, or what I've done here, is I've created a main function, which is basically got an argc and an argv, which we don't, remember, there's no operating system, right? When we're using our computers today and we write a program and we run it, we launch it from our OS. And so our program can exit back to the OS. The OS can parse the different arguments on the command line and put them in a nice place. And so we can interpret them here in argc, argv. None of that exists in a bare metal environment. So all of these are vestigial. That's why we're not using them, and they have underscores. And if we do return an error, it doesn't mean a darn thing because there's no OS or anything to catch the error and say, oh, well, this happened, right? So it is what it is. What happens if your program panics? Well, a crash is an orderly shutdown, right? As you were saying, it sounds crazy with the word panic, but it's an orderly shutdown of your application, and all the resources are returned to the operating system. There is no operating system on a Commodore 64. So what does that mean? So if we ever panic, there's not really a heck of a lot we can do, right? So it's an infinite loop. We're just going to hang. That's what else can we do? So what main does is sets the computer up to be standard. Unfortunately, I just had to include this piece of code. I haven't even tested this because the compiler that I'm using, Rust-MOS, is adding a little bit of feature that nobody asked for. So I'm undoing that. So pretend this doesn't exist. This is just me making sure the computer is in the normal state when my program runs. And I'm going to print hello, and I'm going to address your question about address width. I'm going to define the size of a constant pointer as the value that gets printed here times the number of bits per byte. And it should give us 2 bytes times 8 bits per byte. So it should write 16-bit. And, we want to be very careful because we don't want our program to crash and we care about correctness. So we're not using unwraps here. And in this case, I'm using an unwrap. And then I say, but it's okay because I'm documenting not just to us as humans, but even to the compiler that this code path can't be reached.
So you get that message in your panic message.
If I wanted to spend more bytes, I could write the panic message to, because you can see the panic info. I have data. I could put the message there, but I don't have a lot of bytes, so I'm not spending any on that. So yeah, and that's it. Hello world. So how do we make this? How do we make it go? We're gonna go to my.
Greenline is a ginormous macro, though.
It is ginormous. So fortunately, I'm not using that one. There is another one that's meant to be very tiny, and it will let you do the the string interpolation and so on, but really in a limited way, but doesn't take up a lot of bytes. But you are correct; it is ginormous, so that's why we're not doing that. So I need WesTerm. Where's my WesTerm? I don't understand how it could disappear like that. Okay. So what I'm first going to do is we're going to compile this. If I can move this. Oh, yes, I sure can. Is that sufficiently embiggened? Okay. So I am running Rust-Moss. Rust-Moss is a front-end compiler. It is the equivalent of Rust-C. LLVM-Moss is the back-end compiler. It's the equivalent of LLVM. But the 6502 is so different from every other chip that we use today that they had to fork LLVM to get it to work. You couldn't just have it be a modality, right, of the existing LLVM. Likewise, the Rust compiler front end also had to get forked in order to work with it. It's quite different in order to make it work. It's a minor miracle that it does. The 6502 was, in the Nintendo, what was it? Yes, thank you. In the NES, it was in the Atari 2600. It was in the Apple II. It was in the Commodore. It was in so many computers of this era that there was a lot of pressure from all these different platforms. Like, oh, can we recreate? Can we continue to write software for these platforms? And so this is why this Herculean effort was created to do LLVM Moss. And then one guy said, well, shit, we got to do it for Rust. And he forked the compiler. And once every 2 or 3 years, he updates his stuff and syncs up with the current LLVM mods. So he builds on Linux, and there's a small bug in his build that I've tried for 3 years to fix. Had success once, and it happened to be right before one of his update cycles. Broke me right after he updated. So the best way to get this to work is to run it in a container, and that way the build environment looks and smells and feels like Linux top to bottom. It's just a small bug at the end of a build process on Mac OS or with Unix. So I've created an alias that is basically me telling the build environment inside of Podman to run cargo build. And I have my current project directory mapped into my container. I don't go into the container itself and just write cargo build because I also need to do stuff to copy to USB keys and things like that. So I have a README on this file here, which is kind of providing all the details of what's going on and how to set it up if you want to try this at home. And I will go and do a build. And it built, so that's great. So let's have a look and see what we got. Hello World is a grand total of 273 bytes. Okay, people say, "Oh, Rust is so fat. Rust is this." If you tune your tools, right, you can strip out everything you don't need. This is with those long ass strings in there about how this panic can never happen, and the string interpolator. It's all in there, right? 273 bytes.
Is it really Rust without a panic handler?
It has a panic handler. It's called an infinite loop. It's a beautiful panic handler. What is the other Hello World? Yeah, that's a good question. Let's see, 1953. How can it be the same? I didn't clobber it. Yeah, it is an old one. Oh, it's old because it's underscores. That's why. So they shouldn't exist anymore. All right. So what I need to do now is, in order to get this program over there, I have to package it up in a way that this thing will eventually understand. So there's a command called C1541. And what I'm going to do is I'm going to emulate the floppy disk drive, which was called a 1541 disk drive. And I'm going to format a disk. The title on when I get a directory listing, the title of the disk will be SRUG C64 Rust DE because demo's too long. It's the format of the file will be called a D64 or a disk for the C64, and this file will live one folder above where we're sitting right now in the C64 folder. And specifically, what are we going to write to this disk? We're going to write our binary, right, that we just compiled. So we go ahead, it did that. If I list up a level, we should see our list should be in hello world. There we go. Okay. So that is the file that is representing our program wrapped up in a Commodore 64 disk format. So what I'm going to do is I'm going to copy that to my USB key. Okay. And so I'm going to put it right here in the root of my USB key. So I'm going to say copy. And I like to copy 174K. Yeah. The disks themselves are 180 kilobytes. And so every disk image allocates every block that would be on the physical floppy disk. And we're using 2 of those blocks, right? But what this does is, again, doesn't matter how much stuff we pack in here, the size won't grow.
I bet it zips well.
At this, an empty drive will zip pretty well, or an empty disk will zip pretty well. But if it's full, it'll zip like any other set of binaries. But that's right. So we would like to copy the SRUG C64 demo to the root of our games folder. Okay, and so now when I go back to Finder, I now have a new file here, SRUG 64 Rust demo. So I will eject because Macs don't seem to know how to do that without the actual eject. 2026, we gotta wait. It should just flush all the time, right? Even Windows figured that out.
Is there an erase disk thing on your context menu right below?
Yeah. Yeah. Thanks, usability.
Apple II, because there was a reset button right next to the.
I know, right? Who designs this stuff? All right. So switching over. So if you want to bring the camera around so the folks at home can see. This is my
recording is on.
I got dumped out.
All right.
They can rejoin.
Okay. Well, you can, if you let them know on the Discord that we're back, they can rejoin. Okay. So the maze program, we're writing it in Rust. Again, we're doing this in no standard or no stud, which means that we're running in a bare metal environment. So we won't use stud, but we will use core. What's interesting is the rand crate, which is what we use to generate random numbers in Rust typically, is no stud compatible. If you select it to be default features equals false, it will not use any stud features, and it will compile in a no stud environment. And so I'm going to use a random number generator, a seedable random number generator, because I have to generate random numbers on a Commodore 64. Like, what are you going to use as your source of randomness, right? Like, so anyway, a seedable random number generator, and I'm going to use the small random number generator. This, by the way, RNG is a trait, so I'm going to use a small random number generator which implements this trait, so I can call certain methods on it. So we want to use all the abstractions that we should be using for good solid software. So no magic numbers. The opposite of character string. When I said character string 205, if I were to say what number is this character in BASIC, it's ask, which is interesting because it's not ASCII. So I don't know why it's ASC, but that's the inverse command to the character. So
Ascending?
yeah, I think it's ASCII, but I don't know. Anyway, so 205 is the backslash. And then what we're going to use as our source of randomness is one of the two timers that is inside the machine. Not cryptographically secure, but better than nothing. I'm writing this 16-bit address here. By now, you guys should be getting familiar with 16-bit numbers looking like addresses. So this is also DC, so it's high memory, right? It's not near the bottom. This is one of those devices where we can pick up the timer. So this means probably DC00 is some sort of clock device that's mapped into memory at that location. So what's interesting about the Commodore 64 is if you're writing to that memory location, what's going to pick it up is the device. But there is a full 64 kilobytes of memory, or 64 kilobytes of RAM in this machine. So what you have is you have something that is in front of your RAM, and you can't see your RAM because when you write to it, you're writing to the device. When you read from it, you're reading from a device. So there's other settings where you could disable the devices and get access to more RAM, including your basic ROM, which is probably the biggest chunk of contiguous memory that's available to you. And when you're writing to ROM, because there's no device trying to read it, it goes right through. And you're actually writing to RAM, even though ROM is there. But you can't read it back because you're going to read the ROM value. So you have to disable the ROM to get your RAM values back. And so programmers, demoers, demo scene people, they're all exploiting all of these tricks to get the most out of the machine. You can write to ROM, but you're really not. And they're going crazy with this stuff to get the most out of the machine. So here's where we're going to find our timer device. Here is my ability to read. Okay, so it's an unsafe command in order to read. You're going to use the read volatile method on pointer, and we're going to convert, or we're going to treat timer A. We're going to cast it to a pointer to a U16, and all of this we're going to get back as a 64-bit value. So we're going to read 2 bytes of memory out of the RAM. We're going to take it back. We're going to cast it as a 64-bit value because we're going to have a lot of leading zeros on that. And we're going to use that as our seed to our random number generator here. And then we're going to start with our 205, right? And we're going to add something, either nothing or 1, right? We're now no longer doing anything in between. We're just going to do zeros or ones. And so we're either going to, just like the basic program, we're going to end up with 205 or 206. And what we're going to do here is turn the ASCII value, PETSCII value, into a character. Because if we printed the ASC, we get 205 on the screen. So we're going to turn that into a character, and then we're going to print the character.
And you've got the semicolon again.
Yeah, exactly. Means something different this time. All right, so let's compile this guy.
Does the assembly have multiply?
It does. Yep. And it has divide too, which is incredibly slow compared to multiply, which is still true, but on a 1 megahertz machine, you can feel it. So you quickly learn to multiply by the inverse of something, or, you quickly learn not to do the thing. And today, that's like arcane lore, right? But if you were writing a game in the olden days, you had to know that. That's right. All right, so Moss. And I'm going to do the same thing. I'm going to just build. Actually, I'm just going to go over here to this one. All right, so this time I'm not going to format the D64. What I'm going to do this time is I'm just going to write to it and add our maze program. And then I can copy this to what have you. Okay, that's better. That's what I want to see. And we'll clobber our old version. We'll check the timestamp on it, which will hopefully say very recently. All right, 2018, so that's good. And then what I'm going to do is I'm also going to add one more program to save time. And then after, I'll tell you what it does. All right, so that should also update our timestamp again to
I love the
29.
fact that it also emulates the 2 Unit 8 on the on the Linux side.
On the where?
It said writing file to Unit 8.
Oh, yes.
Honoring the drive
Yeah, well,
convention there too.
yeah. Well, I mean, this is, CBM is Commodore Business Machines, and the C1541 command is designed to make D64s. So, yeah, it's speaking all the lingo.
Did you overwrite the one you had just moved?
Yeah, that's why it's now 2019 is the timestamp on it. So there we go. So there should when I get the directory listing this time around, it'll be 3 programs on there: Hello World, Maze, and Joystick.
Will it? Okay.
Hopefully, unless I've messed it up. Yeah, it basically is. It's a series of files in a drive. It doesn't have folders, so you can't make a folder in that.
Before everything was a bunch of tubes.
That's why. HDMI and USB, not the same. Okay. Hey, one more swap here.
It's still going.
All right, so
Nothing better to do.
stop that. And again, I'll replace the program that's running with the directory, and I list, and nothing should be, or our new program should not be
Why is that present?
Yeah, it doesn't even see the drive. That's what I was expecting the first time. So I will engage the drive. Just gotta wait. Gotta be patient.
Did you remember to eject it?
I did. I
Plug
did.
it back in.
I ejected it safely. I'm not getting the light. I need the.
You get Rust running on at hard drives process. You get Rust running on spinning Rust.
Yep, getting Rust running on the 1541. I mean, this proves you can do it because you can run it on the 6502, and it's actually using a 6502, not even a 6510. So I'm not seeing the light.
People would use their drives as a coprocessor, right?
Yep. All right, so there we are. And now,
There's also no up arrow, right? You can't do this.
Actually, I can't. I just thought that would be confusing if I were to go up and then say list, and then you're like, what? But there you are. There's our 3 programs: Hello World, Maze, and Joystick. So let's load Maze. So I'll use the up arrow, and I can say, and if you shift the second character, L capital O, which doesn't look like a capital O until you switch the character set, that will uniquely identify that as load. And you don't have to write the rest of it. And then I have to go over here and I have to say, then I can say comma 8. and then it's going to see comma 8 space PRG, and it's going to say, I don't know what that means. So I'm going to say, and then there's another command after this. Oops, no shift for colons on this keyboard. And so it's going to execute the first statement, and then it's going to sort of forget about the second statement. And then this will work. Searching for maze, loading. But you see how confusing this gets when you start using up arrow, right? People are like, what are you doing? Can't see it. So LI colon, and then it'll see. So there's our program, right? So let's run maze. Now this one's written in Rust. Notice the speed difference. Whoops. Right? Big difference, right? No, this is 1 megahertz, so it's not like, but this is fast for a 64. Yep. Most of the time now is spent scrolling the screen, right? So, all right. So last one, we've already transferred it over here. Yeah, we'll use the SIMD registers on the 6502 to go faster.
Yeah, this one's right. Yep.
Why is it faster?
Oh, because everything we do in Rust is compiled to machine language. And so the first version that I ran was written in BASIC, which is being interpreted every time. And so that's very slow. And you can think of it like a Python REPL or something like that. All right. So the last one here, do we have anybody in the room?
Just me.
Okay,
It's just the two of us now.
then I will go straight to the code. So the last one here, what I wanted to do is the beginnings of a game. This is where this whole presentation is going. I have a joystick. I want to be able to read it and see what's going on. The joystick plugs into a device that is on the 6502 called a Complex Interface Adapter, or CIA, and we'll start reading that. I don't want to be using magic numbers. So what you'll see here in this code is things like the complex interface adapter is defined as an enum, where you have port A and port B. I'm reading from port B, and I don't need to worry about these numbers. I can do the conversions back to numbers, again in Rust, using a from impl, and I can make sure that my as keyword is not lossy by trying to measure the invariant, making sure it's at least the right size, and so I can be reasonably certain that I'm converting what I think I'm converting. If somebody were to come along later and change this code and make these 64-bit or something, then this would be lossy. We could be throwing away bits that we might care about, and that would be a problem. So I want this to fail to compile if you change your data type. So this is the video interface chip, and here we're naming all of our registers that are on the chip. So I can change the color of the border or the background of the screen. The VIC chip does so many things. It has sprites, it has colors, it has dot addressable graphics. It has a lot of stuff. We're just defining these two. And what I'm going to do here is the same thing. I can convert these to actual numbers, which is what we're going to need to write to memory. But my code can actually function using names and is type safe. So when we look at colors, we define all of our colors the same way. And we then go to our joystick. And our joystick maintains a state. Up, down, left, right, fire, basically. And it has a bunch of methods, basically. I just lost the word. One parameter is something, predicates. Thank you. That's the word I was looking for. A bunch of predicates on here that will tell you what state the joystick is in. Okay. And so all of this, you don't see any inlines. You don't see me doing anything. I'm just making the code, as friendly a developer experience as I can. But this should be adding a lot of fat, right, to the system. So I'm making a new joystick. I'm injecting which complex interface adapter I want it to talk to. And then in an infinite loop, I'm checking the state. And if the state is fire, I am going to turn the border of the screen red. And then when I let go of the button, I'm going to put it back to light blue. Okay, really simple. I have my set border color. You can see I'm writing to the border color, converting it, making sure that it's type safe, and I'm receiving a color to write to. So everything here should type check, and you saw it already compile, but that's what the joystick program is doing. So we'll flip back. Don't have to copy this time. Come on, baby.
There you go.
What's in memory? Old program. Alrighty. Again? Do the same trick again. I don't know what's going on here.
She's getting cranky.
Yeah, it sure is. Pretty sure I didn't already load it. I'm pretty sure I didn't already load it. No, I didn't. Okay. This is the, I'm telling it to jump into assembly language and run in the machine language code that is at this location. So we sure hope it's program and not data. Turns out that this is a well-known memory address to, this is a reset vector, right, for the machine. So it will reset. And then, okay, show me the device.
There it is.
Okay, this one is 1 byte or 1 block. It's even smart. Why? Because we don't have all the print machinery, right? We don't have all of the, bytes of like, oh, this can't possibly panic and all of that stuff. So it's even smaller.
So is it polling the joystick every tick?
It would be polling the joystick. I printed the assembly language, but it would be, yes, effectively it's polling the joystick every clock cycle it can read. So it's going to read, it's going to do some checks, it's going to do a branch. If the branch is going to be favorable, so it doesn't really have a branch predictor, so there's really like but it doesn't also have a pipeline. So it just sets the program counter. There's no stalls either way. Go to the next instruction, and there's the book that tells you exactly how many clock cycles every instruction takes, and it's all deterministic. There's not like, well, if the predictor misses, there's none of that stuff. So it's a very simple processor. So now we're running, and nothing's happening. Dare I press it? Yay! So this is like how you begin to start making your own games, right? Up, down, left, right. You start realizing you forgot about up and there. You forgot about northwest, right? You forgot about the angles. I've written games where I only have up, down, left, right, and I point to the northeast or the northwest, and nothing happens because I didn't program that, right? So I got to go back and redo it. So being able to like begin to build your games and control things with a high-level language and then transfer it to the 64 is pretty cool.
And that's zero cost abstractions at work, because 1 block means under 256 bytes.
It's under 254 bytes
okay.
because the 2 bytes are used to point to the next block of this program.
And that was despite writing high level code in Rust. You didn't pay the cost in executable size at all.
At all.
Nice.
The other thing
Very
that
maintained.
blew my mind about C64 Basic
Yes?
is that it actually reparses every line every time you go to it. So when you go 10 print something and 20 go to 10, right? when it goes back, it actually looks at the text, reparses it,
Oh, see, yeah. Mhm.
right?
Absolutely.
Then it executes it.
Yep.
Then goes to the next line.
That's
because
right.
It doesn't have enough memory to keep the compiled program.
Yep. It's always doing it. It never
No
caches it.
bytecode, no JIT, no nothing.
Nothing, right?
Terrible.
It's simple, right? Like you know exactly what you're getting. So for this guy, I guess that is all I had. I do have a printout of the assembly language for the joystick, and I can show you guys. I think what that looks like really quickly. This is the whole program right here in assembly. So it's well under 254 bytes. But and a lot of this actually has nothing to do with our code. Main has a bunch of stuff to set up. What's really going on is our code is right here, right? And so we're reading, a certain, we're reading,
It looks like it starts by going to 830, which is the DC01 line.
That's right. So this is where we're going to load the current value of the joystick. Then we're going to check to see if the fire button is pressed. If it's equal to a certain value, we're going to go to 82B, which is here. We're going to load this with red. We're going to write that to the VIC2 border, and then we're going to go back and do it again. So this is our code, right?
And the other one means if it's not, do it with the other value.
Yeah, which is light blue, which is 15, yes.
Yeah.
And then write that, and then go back into the loop. Okay, that's it. This is exit code that the program writes. Actually, we never hit this because this is how to exit the program. Go back to basic because this is an infinite loop that never runs. And this is all set up for the main. It's called the prelude for main. So we could actually tell the compiler it doesn't need so much of this stuff, and we could get even smaller. But this is well under 254 bytes.
Excellent.
Yeah. So keep that in mind. All right. Thank you, guys.
Thank you so much.